I'd like to talk in this lecture about the virtual trackball, and I branded this as a optional lecture, but I really think you all ought to look at it, and especially as with the last one, I really want all the graduate students and anybody who's taken 412 already to look at this lecture. But the value of it is that we want to have more graphical kinds of devices. In a way, you've seen them because the buttons that we've been working, slide bars that we've worked with, are graphical devices. You interact with the device. But there's another way to look at things, and that's this idea of direct manipulation, where you actually use your mouse or some other device to directly work with the object. And that's something that was really lacking in our previous lecture when we talked about the rotating cube, because in order to change the rotation, what you did is you pushed buttons rather than work with the device. And if you wanted to do something a little more interesting, you really couldn't do that. So let me show you where we're trying to get with this. And this example was done using C++ and a shader-based desktop OpenGL that I did, I think, a couple of semesters ago. And I'll try and figure out where to get all this code and put it someplace where you can get it, because I'd really like you to implement it in JavaScript with WebGL. But let's just take a look at what this difference is, and let me see if I can get to it. Yeah, here. So here's the cube again, and I don't have any buttons here. But what I'd like to do is to be able to point at the device and then point at the object and then move it. So I'd like to be able to do stuff like this. I'm just using the mouse to rotate it about. And even better than that, if I give it a quick little jerk here, I can actually start it spinning. I can just click the mouse again and hold it and go back into this mode. And that's a much nicer interface and a much more useful interface. And so we'd like to be able to figure out what do I have to do to bring that kind of interface to our applications. And it turns out it's a wonderful example of some of these ideas we've been talking about rotation and doing it with quaternions or doing it with standard transformation matrices. So let's look at constructing a virtual trackball that can do these kinds of things. Okay, so one of the things we're gonna see here is again that using something other than direction and Euler angles is going to really help us here. It's a nice application to transformations, and hopefully if you develop this, and you'll be able to then bring this virtual trackball into any application that you do later. So let's start with just looking back at the physical trackball and say, okay, here it is as kind of a mechanical mouse upside down. It's this platform, and this ball is embedded in it, and you can hold your palm down on the top of it and move it a little bit and in two independent directions, and get that motion back to the computer. Or if you move it a lot, it's sort of a variable sensitivity device. You move it a little bit, then the way it's used is you don't change anything very much, but if you move it a lot, it changes. For example, in the cube, it changed some angle a great deal. But if you think of it as having little friction, and sometimes you can control this with a mouse or with some of the wheels on mice let you do this, or if you had a trackball with essentially no friction, you could use your hand and then spin the thing, and that's how you get continuous input from the device, and we can use that to keep something moving. One way to think of it is that there are two different modes. One when you're pushing on it and just moving a little bit, and the other when you just spin that trackball. So how can we get that? Well, without having a real trackball, and even having an idealized trackball that has no friction. Well, here's how we can get it from a mouse to try and get these two modes. And what we're going to do is move the mouse, but we're going to convert the position of the mouse to a trackball position, a position of that ball, or actually it's half the ball you want, and then we'll look at the event listeners that we need to make this whole thing work. I'm actually not going to derive the event listeners, that's for you to do, but I'll tell you what the event listeners you need are and what they do. Now, here's again an example, as I said, of using quaternions because we're going to convert to rotations about a great circle. And that makes sense because here you have this ball, which is a sphere, and great circles on a sphere have a very important property that they're the shortest distance between 2 points. Now the code that I'm going to try and find for you, and I'm sure you can all find it by search, is Silicon Graphics long ago made virtual trackball code. So I think if you just do some searches on trackball, you'll eventually dig up some C code from SGI. It's probably 20 years old now, but that uses quaternions in it to do the rotations. Now, if we switch this over to WebGL or any shader-based OpenGL, then it's really nice because the quaternion shaders are very, very simple to construct, and I'll show you an example of that at the very end of this lecture. So let's go back to the trackball, and here's a physical trackball. And say I impose a frame on that where the origin of that frame is right at the center of the ball, and we adopt an X, Y, and Z direction. Maybe a line with the base, and the Y direction we'll say is pointing up. Now, this is a very special case of projection in the sense that I can go between 2 and 3D go uniquely, because I'm only interested in going between positions on a plane and positions on the surface of this ball. So let's see that in this slide. So what I want to say is that convert is that if I have a position from the trackball, which is a position in the plane, I'm going to project that straight up until it hits the trackball. Let's assume it's all within the positions I'm moving in, or within this circumference based on the radius of the sphere. So given an xz0, a position of the mouse in this plane, how do I get this xyz? I go straight up and use the fact that this ball has a known radius r. So let's look at the equation you get. So this is just saying what I just said, that we can reverse this projection direction. Instead of going down from the ball to the plane, we're going to go from the plane up. And if I take that xz value in the plane y equals 0, it corresponds to some point on the surface x squared plus y squared plus z squared equals r squared. So when I solve that for y, I get an equation for given an x and a z. Here's the corresponding position up on the surface of that hemisphere. And that's really the crux of it. Once you've done this, now as you move the mouse, it's like you're giving positions on the surface of the trackball. And I can now say, okay, suppose I have 2 points that I have on that surface, which I get from either clicking the mouse twice, or more likely by doing an operation where I hold the mouse button down, and I'm continually getting feedback from the mouse that's giving me positions. But it's giving me a sequence of positions as I move the mouse, which correspond to points P1 and P2 on the surface of the virtual trackball. Well, if I look at that in terms of the great circle and shortest distance between P1 and P2, the picture kind of looks like this. I project up to P1 for the first mouse position. I project up to P2 for the second mouse position. And then that determines a great circle between the three. Now notice that this is a unique plane because defining a unique plane because I have 3 points on the plane. I have the origin down here at the center of the sphere, and I have these 2 points. So therefore, that's determining a plane that cuts through the hemisphere and gives me that great circle. But the more important thing is that because I have a plane, I have a normal to that plane, a distinct normal. And how do I get that normal? Well, I can take the 2 vectors. And what are the 2 vectors? Well, I can go from the origin to this point, determining a vector we'll call P1 now, and I can take the second position minus the origin position. That gives me a vector P2. Their cross product is going to be normal to the plane, and now I have from the 2 positions that I've gotten from my mouse projected up onto the hemisphere, now giving me this normal. Once I have the normal, I can now compute the angle that I have to rotate about this normal in order to go from P1 and P2. So that's the angle. Now how am I going to get that angle? Well, I can get the angle from the cross product. There's the relationship with a cross product that if I take the normal of the cross product and divide it by the normals of the two vectors I used to get the cross product, it gives me the sine of the angle between them. You know, the relationship you're more familiar with is the length of the normal is the length of the first vector times the length of the second times the sine of the angle between them. But I can do even better than that, because if I'm tracking continually, then I'm getting these positions P1 and P2 that are actually very close to each other. This is called mouse movement as opposed to mouse click. That I'm getting continual motion. I'm doing continual motion, generating this measure back to the device, and you could figure out how to do that, I think, fairly easily with listeners. And now, once I've done that, I can say, well, if it's giving me P1 and P2 very spaced very closely, then I'll use the approximation that sine theta is approximately equal to theta. So I don't even have to use any trigonometry to do that. I use this approximation, continually updating theta. That's the theta that I'm going to use now to rotate my cube or whatever other device is being controlled by this virtual trackball. So this converts to, and notice how this fits with quaternions, because quaternions are, what are they really good at? They're really good for doing rotations using great circles. So I don't even have to go to the matrix formulation. If I can write a quaternion shader, then I can do this all within the shader by just passing in the angles or actually passing in the proper quaternions. So this all works out very well, and it was a very standard application of quaternions. The kind of listeners that you need to look at, because you have these two things going on where you want to, one hand, look, if you're not moving the mouse, you want to continue you may want to continue the rotation and have the thing continue to spin as if the device were frictionless. You want to be able to either track the mouse or not track the mouse position, and you want to be able to say, hey, am I supposed to update the rotation at this point, either through a matrix or through a quaternion. So if you put this all together, you should be able to write the code, and once you have it, you'll have a wonderful interactive direct manipulation device you can use in all your applications. So let me finish up by just showing you one or two slides that I happen to have. This just sort of shows you how simple a quaternion shader is. That if I can, as I said last time when we were talking about this, you can have functions in your program object in addition to having the two mains for the vertex shader and the fragment shader. So here's a quaternion multiplier that takes in a vec4, but now the vec4 represents not a position or a color, but rather represents a quaternion, the four constants that determine the quaternion A and the four constants that determine the quaternion B. And so all it has is one line that returns a vec4, which is, and this is exactly the formula that we had when we talked about quaternions. And also notice that dot and cross are functions that are built into GLSL, so you don't even have to write those things yourself. Here's a direct one-line quaternion multiplier, and the rest of the shader kind of might look something like this. Here's the inverse quaternion function if you're going to need an inverse, and here would be a quaternion fragment shader that would take the quaternion coming in as a point and then do a rotation you put in the rotation quaternion, and now you can do rotation. Now remember what rotation looked like. It was the product of three quaternions. It was, so you can multiply the point times the inverse of the rotation quaternion and pre-multiply that by the rotation quaternion. That gives you the new position. So here's how you do it. It's very straightforward. Notice you get, because it's returning vec4s, you can chain all this together very nicely. And now we have to convert back from the quaternion back to a position in XYZ space, but that's easy, because if you remember how we looked at the quaternion, its first component, there was a scalar component, and we represented a point by using the next three components, the y, z, w of this quaternion that I created, and then the fourth component is going to be a 1 because this is the representation of a point. So we're going back to homogeneous coordinates by using this little swizzling selection operator. So give you something to think about, and I hope at least some of you actually implement this.